My name is Laerte and I'm from Federal University of Minas Gerais. Today I'm going to present the paper Beyond the Code, Mining Self-Admitted Technical Debt in Issue Tracker Systems. This paper was published at MSR 2020. Well, in software development, the done is better than perfect maximum reflects the usual challenge of releasing fast and keeping software quality. In this context, the technical debt metaphor refers to the maintenance and evolution costs of such not quite right solutions. In this case, the self-admitted technical debt, also known as SATD, is a particular case of technical debt where developers explicitly acknowledge their suboptimal implementation decisions. In the example shown here, developers from Microsoft VS Code admit a temporary solution by commenting the code with an indication of hack. To the best of our knowledge, SATD studies rely on source code comments to identify TD instances by searching for keywords like fix me, to do, hack, and so on. We denote this current practice as SATD-C. By contrast, we believe that developers can acknowledge technical debt beyond the code. So, we investigate the practice of admitting technical debt by creating niches to document suboptimal implementation decisions. In this case, developers label these issues with terms like technical debt or debt. In the example shown here, we observe an issue also reported at VS Code to highlight an existing workaround. As we can see, the issue was marked as a debt label. Therefore, in this paper, we denote this issue-based type of SATD as SATDI, and then we propose 4 research questions to investigate this novel SATD type. They are: what is the overlap between SATD-C and SATDI? What types of technical debt are paid in SATDI? Why do developers introduce SATDI? And why do developers pay SATDI? To answer to these questions, we study SATDI instances from 5 open source repositories, GitLab Community Edition, and 4 GitHub-based systems. At first, we selected GitLab because it's a well-known open source platform that we already have previous knowledge about its practice to document TD-related issues with a technical debt label. So we started to build our dataset by selecting GitLab's issues marked with the technical debt label and closed in the last 6 months before our study. The idea behind this 6-month time frame was to increase confidence in our survey results. As a result, we first found 188 issues that filled this criteria. Next, we removed issues related to discussions, feature requests, bugs, and also issues that were ignored or closed due to duplication. In the total, 71 issues were removed. Finally, we selected 117 SATDI instances from GitLab Community Edition. Next, we also decided to search for SATDI in GitHub systems. For that, we first restricted our search to issues from the top 5,000 most popular repositories, issues that were tagged with labels like technical debt or simply debt, and also that were closed in the same 6-month time frame. We also discarded repositories with less than 10 TD labeled issues. The idea was to select repositories which had the common practice of labeling TD related issues. Finally, we selected 4 GitHub-based repositories from which we retrieved 218 issues labeled with TD-like labels. And just like we did for GitLab issues, we performed the same manual inspection and removed 49 issues. In the end, 169 SATDI instances coming from 4 GitHub repositories were selected for inclusion in our dataset. Therefore, in this paper, we studied 286 SATDI instances by performing 3 complementary studies. In the first study, we aim to answer research question 1 by investigating the overlap between SATD types. In other words, the goal of this study was to analyze our SATDI instances to verify if there are also code comments admitting the same depth. To accomplish that, we first inspected the pull and merge requests responsible for closing our studied issues. In GitLab, merge requests are equivalent to pull requests. And so, specifically, we first collected the pull and merge requests used to close our issues, retrieving the diff of each associated commit. We then analyzed all the deleted lines from these commits to investigate if there were comments indicating SATDC. Finally, we used SATD Detector, a tool provided in the literature, to automatically identify SATD-related comments. Among the 286 analyzed issues in our dataset, we found that 167 issues were closed by an associated pull or merge request. Besides, we also observed that these pull requests included more than 4,700 diff chunks. We then analyzed all of these chunks by applying SATD Detector. As a result, the tool identified code comments indicating technical debt admission in 48 issues, which represents 28.7% of our dataset. Therefore, in our first research question, we observed that many SATD instances are documented beyond the code. In our second study, we focus on classifying the types of technical debt paid in SATDI. For that, we first defined 10 SATD types based on categories used in the literature. For example, we classified technical debt related to intra-method design and high-level architecture as design debt. Other categories involved TD related to tests, performance, or infrastructure issues. In fact, our first round of classification showed that design was the most popular case of SATDI, and because of that, we decided to perform a subclassification of these issues by defining 4 additional categories related to specific design problems. For example, we included the complex code and architecture categories to classify intra-method and high-level technical debt, respectively. Finally, we performed closed card sort to classify our studied issues. To apply this technique, 3 authors of this paper manually analyzed a subset of the 286 issues and classified them in one of the selected categories. At the end, each issue was analyzed by 2 independent authors. Also, conflicting categories were discussed to reach a consensual classification. As a result, we found that 169 issues were related to design debt. Other categories were less frequent. For example, TD related to tests had only 25 occurrences. Among the 169 SATDI related to design, we found that 74 were related to complex code, 57 to architecture, 32 to cleanup, and 6 to code duplication. In this example shown here, we observe an intra-method SATD documented in Neuromi Sailor's issue tracker. As we can see, it was classified as a complex code debt. By contrast, the issue presented here was classified as an architecture debt since GitLab developers documented the need of refactoring a long class. Finally, from research question 2, we may conclude that SATDI is mostly paid to fix design flaws. Lastly, to understand the reasons why developers introduce and pay SATDI, we conduct a survey with developers. In this case, we selected from our dataset developers with public email address who were responsible for closing a specific issue or accepting a pull or merge request that closes the issue. For each developer, we sent a unique questionnaire presenting the last technical debt-related issue closed by the developer and proposing 3 questions. The goal of the questionnaire questions were to investigate the reasons why developers pay technical debt, to discuss maintenance problems caused by technical debt, and to understand the intentions behind the inception. From the total of 286 issues, we retrieved a list of 85 distinct emails, from which we received 30 answers. That represents a response rate of 35%. So, for research question 3, we observed that most of the studied issues were introduced by developers to ship earlier. In 9 cases, developers were not aware of the technical debt when it was introduced. Finally, 6 other developers provided various motivations. As an example, developer D16 discusses the practice of introducing technical debt to speed up development and release fast. By contrast, developer D15 indicates that the SATDI that he paid was a consequence of the unplanned growth of the system. Therefore, we may conclude that SATDI is usually introduced as a deliberate choice for agility. Finally, in research question 4, we observed that developers mostly pay SATDI to reduce TD interests and to clean code. In the example shown here, developer D7 indicates the benefits of a cleaner code as a motivation for paying SATDI. As a conclusion, we may indicate for research question 4 that developers usually pay SATDI to deal with TD interests and to clean code. Finally, we may wrap up this paper as follows. First, we identify and study SATD beyond the source code, detecting and mining initial tracker systems. For that, we collected a dataset of 286 SATDI from GitLab and GitHub repositories and performed 3 complementary studies. We showed that only 29% of the studied SATDI instances can be traced to SATDC. We also indicate that almost 60% of the studied issues refers to design flaws, and that technical debt was deliberated introduced in 45% of the issues. We also conclude by showing that developers usually pay SATDI to reduce technical debt interests and to clean code. Thank you for watching this video. You may reach me for questions and suggestions by mail and Twitter. Bye bye.